All right, welcome to 3.1, Solving Systems by Graphing. Our essential question: how do you solve systems of equations by graphing? You have looked at these before. They are useful in real life, especially when you're trying to figure out what the break-even point is. Like when does it not matter either way? You think of like gym memberships and airline flights. Like at what point is Spirit not a better deal because they charge you for every single thing? So like if I have a check bag, like maybe Delta ends up being better in the long run, based off of what you need in your flight. These are useful. I have used them in real life. Maybe you won't, but I have. So all right, some vocab before we get going. A system of linear equations, that's just a set of two or more linear equations. And remember, a linear equation, an example of that would be like y equals, x plus 3, where the graph is a line, or maybe y equals 2x minus 7, right? This would be a system of linear equations, because there's two or more. All right, solution of a system of linear equations. Well, the solution we're going to put into an ordered pair, and they're an x and a y value that makes all of the equations true. Okay, so we would find an ordered pair x comma y, and if we plugged in the x number and the y number, it would work out in both situations. Okay, and when we solve this graphically, what it looks like is that, so in this example, we have y equals 2x here, and we have x plus 1 here, and right here at 1 comma 2, this is our solution because it works for both this line and it works for this line. We're going to look at the intersection point of those of the lines. All right, so solving a systems of equations by graphing. First off, we're going to graph it, and then we'll find the intersection point, and then we'll check it just to make sure it works. Okay, so the first one I'll do maybe in red. So 2x minus 1. This will be our red one. So our y-intercept is at negative 1. And then we go up 2 over 1, up 2 over 1, up 2 over 1. That's probably good enough. I'll try to get a line going here. Something a little bit like that. There we go. That looks better. Okay. So I'll maybe make that line red if I can. There we go. All right. Now we'll do maybe a blue one. So we have negative 7 is our y-intercept. So 1, 2, 3, 4, 5, 6, negative 7 down here. We're going to go up 4 over 1, up 4 over 1, up 4 over 1. And you can see right here, I just put a dot that's on that line already, right? And so let's make this a blue line here. Something a little bit like that. There we go. Okay. Now we were talking, we can see our intersection point is right here, right? And so our solution here, the intersection is at 1, 2, 3, comma, what, 4? 1, 2, 3, 4, 5. 3, comma 5. So this would be our solution. Now let's check it just to make sure it works. Okay, so with the red one, we're going to put in 5 for y, 2 times x is 3 minus 1. Oops. So do that there. Oh no. There we go. Okay, and so then we solve it just to make sure it works. This would be 6 minus 1, and so yes, it works here. We're good. Okay, now check it in the blue equation. Again, we plug in 5 for y, we plug in 3 for x, minus 7. 5 equals 12 minus 7, and so again 5 equals 5. We're good to go, so it does work. Alright, so what is the solution of the system? Now, I'm going to get these both into y equals mx plus b. It's just way easier for me. This one already is, but this one, I don't know. I'm just going to get into y equals mx plus b. Okay, so I'm going to subtract my 2x from both sides. And so I'm going to get negative y equals negative 2x minus 1, which when we divide by negative 1, we get y equals 2x plus 1. Okay, so that's one of my lines, and then I'm going to just write my other line here. Y equals 1/2 x minus 2. Okay, so those are our two lines. I'll start graphing the green since I'm already in that color. So we got minus 2, and then we're going to go up 1 over 2, up 1 over 2, and that's probably good. A little green action going here. Okay, there we go. And now for the blue one, we're at plus 1. And we're going to go up 2 over 1, up 2 over 1. Now, as you can see, I'm getting farther. they're diverging, right? They're getting farther apart. So let's actually go down 2 into the left one, down 2 into the left one. And you can tell, you know, if I had gone this way with my green dots, I'd be down 1 over 2, and my intersection would be right here. So let's get our line going. Okay, and so we see our intersection point is at, let's see, 1, 2, negative 2, comma, 1, 2, negative 3. Okay, now just to check, it's always good to check. We plug them in for both. So negative 3 equals 2 times negative 2 plus 1. Negative 3 equals negative 4 plus 1. Negative 3 equals negative 3. So that one's good to go. The green one here real quick. Negative 3 equals 1/2 times negative 2 minus 2. Negative 3 equals negative 1 minus 2, which is negative 3. So it works for both. We're good to go. All right. So writing two systems of equations. Suppose one puppy weighs 5 pounds at birth, and then they grow at a rate of 0.25 pounds per month over the first several months. Okay, so let's first off write that in an equation. So they start off, we'll say just y equals, okay, they start off at 5 pounds. Okay, so we know we have a plus 5. Okay, because that's their starting point. Now, they grow at a rate of 0.25 pounds per month, so 0.25 per month, and we'll call it month X. Okay, so that's the first one. Okay, and then we'll do another puppy. They weigh 4 pounds at birth, and they grow at a rate of 0.5 pounds per month. Okay, so we have y equals, now they grow at 0.5 pounds, so 0.5x, and they started out at 4 pounds at birth, so plus 4. Okay, now we graph them. I'm going to start with red, 1, 2, 3, 4, and we go, now really this is 1/2, right? And this would be 1/4, so we're going to go up 1 over 2, up 1 over 2. I might as well go down 1 into the left 2 while I'm at it. Get our line going here. There we go. And then the black one, I remember this is just 1/4, right? And so we start out at 5, which is 1 above. And we're going to go up 1 over 4. And hey, looky here, we have our intersection point already. So that's good. Okay, and so then I'm going to just real quick draw my line. Perfect. Okay, and we see that that's the intersection point. And so when we find it here, 1, 2, 3, 4, comma, 1, 2, 3, 4, 5, 6. 4, 6 is our solution. Okay, we're not going to check this because we're running a little bit low on time, but you should. All right, vocab here. Types of systems of equations. If it's consistent, that means you have at least one solution. That's good. Independent would be exactly one, and dependent would be infinitely many solutions. So it works no matter what. Independent, exactly one. These have been independent solutions because they intersect at one point. Okay, so intersect at one point. Okay, infinitely many would be, they're the same line. Okay, that would be like you have your graph and then one of the lines is like this, and then you have your other line which is like exactly the same thing. There's infinitely many solutions because they cross no matter what. Okay, and then no solution, that would be like parallel lines, because they're never going to touch, right? There's no intersection points here. All right, so solve each system by graphing. Tell whether the solution has one solution, infinitely, or many, or no solution. Okay, so we're just going to think about this here. For this one, our y-intercept is at -3. So already this one's out, right? Because it doesn't intersect at negative. Oh wait, yes it does. I'm so sorry. Undo. Okay, so this one, they all cross at -3. Our slope is -1, so we're supposed to be going down 1 and over 1. It's supposed to have a downhill slant to it. Okay, so this one's out because the slope is negative. Okay, now for the other ones, they both intersect at -3, and they seem to appear to have the same slope here. So let's just take a glance at the slopes for both of these lines. We have the same slope, don't we? And so when we have the same slope, that indicates that they're parallel, right? And so B would be our solution. The lines are parallel, and the system has no solution because they never intersect. Right? So now we're going to determine without graphing whether the system is independent, dependent, or inconsistent. The first step is to get them both into y equals mx plus b, and then we can go from there. Okay, so for this first one here, let's subtract 3x, and so we get -4y equals -3x plus 6. And then we got to divide by -4, divide by -4, divide by -4. We're running a little bit low on time here. This would be positive 3/4 x minus, and then if we reduce it, we get 3/2. Okay, now for the blue one, all we have to do is divide by 8, right? And so y equals 6/8 x plus 3/8. And this reduces down to 3/4 x plus 3/8. Okay, now all we need to do is we need to look at the slopes. Same slope, isn't it? And so we know that they're parallel. And so there's no solution. They're going to be running kind of like this, and so it's an inconsistent system. If the slopes are different, that's a good sign. If the slopes are the same and the y-intercepts are the same, then it would be infinitely many. All right, so this one, we don't even have a number for. I must have accidentally deleted it, so we'll call this the end of the video. Basically, same slope, and same y-intercept. Be infinitely many. Okay, if they have different slopes, that's good. That means that we have a solution, one solution. they have the same slope, then you know that they are parallel, and so then there's no solution.